Okay, we have just learned about how we can use tree diagrams and tables to list out a sample space in a compound probability or compound event situation. And we learned from that we can actually multiply the number of choices we have for our first choice times the number of choices we have for our second choice, and it will give us our total number of outcomes in our sample space. Well, this actually has a name. It's called the fundamental counting principle, and it's what we're going to learn about today. It says if event M has M possible outcomes, and event N has N possible outcomes, then event M followed by event N has M times N possible outcomes. So that's just crazy, right? It's, say the first event is flipping a coin. There are two possible outcomes for flipping a coin, heads or tails. The second event, let's say, is rolling a die. There are 6 possible outcomes of that second event. If I multiply that together, that gives me 12 total possible outcomes. This is the fundamental counting principle, also called the FCP. It says you can use multiplication instead of making a tree diagram to find the number of possible outcomes in a sample space. This is called the fundamental counting principle. Example 1. It says find the total number of outcomes when a coin is tossed and a number cube is rolled. Oh, there you go. That is what I just did. The total possible outcomes from a coin being tossed is 2. The total possible outcomes from a die or number cube being rolled is 6. If I multiply them together, then the sample space would have 12 total outcomes in it. And you can see below that if they made a tree diagram of this situation where heads is your first possible outcome, tails is your second possible outcome, and then you branch off to the numbers 1, 2, 3, 4, 5, and 6 from each one of those, then your sample space would have heads 1, heads 2, heads 3, heads 4, heads 5, heads 6, tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. That would be 12 different outcomes in the sample space. Down here in letter A, it says find the total number of outcomes when choosing from bike helmets that come in 3 colors and 2 styles. How many possible outcomes would that give you? You can do that one on your own, probably before I can change this slide. Find probability. You can use the fundamental counting principle to help find probability of events. Example 2. Find the total number of outcomes from rolling a number cube with sides labeled 1 through 6 and choosing a letter from the word numbers. Then find the probability of rolling a 6 and choosing M. Well, first thing we got to find out is how many possible outcomes are there from rolling a number cube with the sides 1 through 6 and then choosing a letter from the word numbers. The cube has 6 sides on it labeled 1 through 6. So there are 6 possible outcomes from that. The word numbers has how many letters in it? 1, 2, 3, 4, 5, 6, 7 letters in it. So there's 7 possible outcomes from choosing a letter from the word numbers. I multiply those together and I find out that there are 42 total possible outcomes in the sample space. So, how many of those outcomes, how many of those 42 outcomes do you think is rolling a 6 and then choosing the letter M? So what is the probability of 6, M? Well, we learned yesterday that when we do a sample space, that each one of the results in the sample space is unique. It's different from all of the others. Well, if that's the case, then only one of the results from this sample space would be 6, m. And there would be 42 total in the sample space. So the probability of 6, m would be 1 over 42. Not very big chance, huh? Let's take a look at example 3. It says find the number of different genes available at the gene shop. Then find the probability of randomly selecting a size 32-34 slim fit. Is it likely or unlikely that the genes would be chosen? So let's take a look. How many choices of waist size are there? There are 5 choices of waist size. The length has only 3 length sizes. But then there are 3 styles. There's the slim fit, the boot cut, and the loose fit. So there are another 3 choices. In order to figure out how many total different styles and waist sizes and length sizes we could get our genes in, we would multiply those together using the fundamental counting principle, the FCP, and we find 5 times 3 is 15, times 3 is 45. So there would be 45 different size and styles of genes that we could choose from. So what would be the probability of getting a 32-34 slim cut? Well, out of the 45 different pairs of genes that the shop offers, only 1 out of every 45 would be a 32-34 slim, since each one of those 45 different pairs of genes would be unique and different. So it's 1 in 45. How likely is it? It's very unlikely. Let's take a look at example 4. A box of toy cars contains blue, orange, yellow, red, and black cars. A separate box contains a male and female action figure. What is the probability of randomly choosing an orange car and a female action figure? Is it likely or unlikely that this combination is chosen? Well, let's first look at our compound events. It says we're going to choose a toy car, and there is blue, orange, yellow, red, and black. How many colors are there? 1, 2, 3, 4, 5. We know that there are 5 color choices. How many? And then it says a separate box contains a male and a female action figure. So how many choices of action figures do we have? We have 2, a male or a female. So how many total possible combinations are there? Well, that would be 5 times 2, or 10 total combinations in the sample space. And it says out of those, we want to know what is the probability of choosing orange with a female action figure. Well, out of all the possible combinations in the sample space, only one of those would be uniquely the orange car with the female action figure. And so it would be 1 out of 10, which is about, or which is 10% of them. So it's not very unlikely like in the previous problem, but I would still say this is an unlikely situation.